Hello, Ken.
Hello. How are you doing this morning?
Yeah, good.
Yeah, I'm doing okay. Tired.
Half of your stress is from me, I guess. So I cannot tell you.
Yeah, I'm trying to get everything done, and then the exam I have today too. So.
Have I mentioned to you about hot porridge seminar?
No. You said a seminar?
Yeah, so let me give me a. Yeah, so um, so the math department here, mathematics department, there is a faculty in UX, he goes by the name Jersey coaching. But he also so he's a faculty in the math department, mostly interested in geometry, and he runs a seminar. It is a very friendly seminar, unlike like many of it's not the formal. I shouldn't say other seminars are not good. It's just that it's over friendly. It's a group of people. Most of it is like from 3 to 4 faculties that come together and have a, have a seminar pretty much every Thursday. So this is called Hot 40 Seminar. So as the name suggests, you can talk about anything in there, but mostly mathematics and physics. But actually engineering also, I should say. So there are some faculties coming from the engineering department also. Again, it's a very small group of people, but friendly people. And I mention it because today I'm giving a talk in there. Again, it doesn't mean that you should attend. It is not a course requirement. It is surely you won't gain anything as far as this course goes from that. But I'm talking about something very simple. If you have a car wheel, so these are the two front wheels and back wheels of the car. Right? So that's your car. And you can ask, what's the direction of friction on these wheels? Like, does the friction act in the backward direction or in the forward direction? You might have wondered about this before, and how do you analyze that? It's relatively elementary as far as physics course goes. It's often done in introductory physics courses, but it doesn't hurt to go over it again. So that's what it is. Okay. It is these days held on Zoom, and if you're interested in attending, send me a one-line email and I'll send you the link. Okay, I don't remember the link as such uh, with me. Okay, is that clear?
Yeah. Do you happen to know what time?
Oh, it's 2 p.m. Thursday. Most of the Thursdays 2 p.m. Today, basically. Yeah, you might be teaching, so don't feel like again. I'm telling you should not make you attend it only if you're interested in the topic or if you're interested in just knowing people. Like these are just a friendly set of people. But again, friendliness depends on what kind of thoughts you have. So that is important. So just I would say check out, like there are some old these days because of the Zoom. Many of the talks are available online, so you can go and look into it and see how it is. And if you like it, start coming. It's pretty much like a circle you form, right? Is that clear?
Mhm. Yeah, yeah. Unfortunately, I do teach at 1 p.m.
Yeah.
till
So
3.
yeah,
But
just
I think today they'll get done pretty early. I think the lab's pretty short. So if I can make it, I definitely will do.
yeah. Again, don't feel obliged to do it just because I'm telling you. Okay.
Okay.
Yeah. So only if you have time for these things you need to do it.
No, no. I mean, I am really interested in multidiscipline kind of seminars and stuff. Thank you.
So that might give you an idea of what it is. Yeah. Yeah. So okay. Again, it's not clear just because they are attending how it should be, but that's what it is. Okay. I think I told you sufficient. Yeah. I thought I should have mentioned this before, just as a advertisement for the talk. But yeah, feel free. Okay.
Okay. Thank you.
So I posted a homework. This is unrelated to the course. So this is homework 12. Is due April, cannot be April 20th because I said there's no class, right? Thursday, and remember, new class on April 20, which is Tuesday.
I actually have a question.
Yes.
Will you still be available to meet that day, or is that being
No,
pushed
no,
up?
no. I'm out of the campus. That is why I have to take a holiday. Uh,
Understood.
yeah, I have to be present in a court or a yeah formal setting, uh, which requires me. I have to be there for my own requirement. It's not a government requirement. Yeah.
Okay. Okay. So
So
sorry.
I won't be available on that day. But if you want, I think I should be done by afternoon or something. So if you want, we can get on Zoom if it is important. Otherwise, before or after. So Monday or Wednesday is the right time then. Does that?
Okay. So like, yeah, yeah, that's clear. Monday, like 9 to 11 is still okay.
Yes, 9 to Monday. No, no, no. Yes, Monday 9 to 12 is still okay. That's correct.
Okay.
Exactly.
Cool. All right.
So
Thank you.
yeah. So just if you let me know, uh, I'll make sure that I'm here in the campus because I know you prefer to meet in person, right?
Yeah.
So if you want to meet me in person, I typically stay at home and say that meet me on Zoom. That is what I do. But if you let me know before, and I'll just show up here. I work there or here. It doesn't hurt me at all. Okay.
Okay, yeah, I'm gonna be doing a lot of stuff this weekend as far as like homework and stuff. So I just expect to have a lot of questions.
Sure. Yeah.
But I'll
So
send you an email. I'll let
yes.
you know.
Yeah. Please send me an email so that I'm aware. Okay. Or email helps me. It's a promptness. I kind of do that. Yeah.
Thank
Okay.
you.
Okay. So we did precision of the perihelion, and that's all we will do as far as Kepler problem is concerned. We had to do it short, or I wouldn't say very short. We could have done more details, but since we did precision of perihelion, I think it's a good amount of stuff. Probably we went through it a little in a hurry. We could have done it more slowly, spread out in 2 lectures, and it would have penetrated more. But mostly that's all we have for a Kepler problem in this course. And now in the remaining 4 days of classes, right, since I'm missing on Tuesday, it will be 2 of the Thursdays and then 1 more week of classes, right? So 4 lectures. I want to do what we describe as special theory of relativity, right? This is Einstein's extension of the relativity principle, and which was profound in the sense it changed a lot of the way we look at space and time, and most of our theories came out of that. Correct? So, so broadly, this is special theory of relativity. And I expect that you've seen it in some form or the other at some introductory level, probably not as much detail as we will do here, but you probably are aware of time translation. No, what I meant, no, not time translation, time dilation and length contraction, right? And how velocities, how there is a maximum speed information can travel with, and how energy can behave like mass. Okay, uh, uh, have you heard of these very broad concepts?
Yeah, I took a class on modern physics and it covered a lot of those concepts. So.
Yeah, perfect, perfect. Okay, so very broadly, this is about uh, uh, speed limit, let's say, very popularly speaking. So this is about speed limit. This is about the nuclear bomb in a sense. So energy is the same as mass, right? And that has a big consequence. Remember, mass attracts another mass. So you can say that, or let's me think of it like this: mass, yeah, mass attracts another mass. But if you replace the other small mass with energy, that means to say it can attract energy, which is a little harder concept when you come out of Newtonian physics, like photon, for example. Photon is a piece of energy. It doesn't have any mass associated with it. So will it attract photons? And yes, the conclusion later on will be that in a more advanced version of relativity is that yes, it will attract. And then we have length contraction, time dilation. So time dilation is the idea that if you're moving faster, the time, the actual your time, I mean, you feel you will be younger in that sense. Time decides our lifetime. So we will live longer if you're moving around, but you have to move around significantly fast to have any significant uh, consequences in that. And velocity addition, that's incorporated in speed. So this is very, at some popular level, these are the words that will catch your attention. But we want to talk about today here the principle of relativity. So let's say relativity. Which is the first statement out of which everything, all the above comes in. And what we will do is here, so what is a summary of what we are going to do in the next 4 lectures? We are going to do pretty much the whole of the introductory level Newtonian physics, rewrite them in a way which is consistent with what we will define as principle of relativity, which I assume you have seen it in some form in introductory level physics. So for example, the definition of velocity, acceleration, and force equal to mass times acceleration, energy, momentum, all these definitions we want to revisit and not necessarily change everything, but at least make it consistent with whatever we have. The primary ideas that will change is the idea of energy and momentum. Velocity and acceleration will stay the same. Okay, those definitions will stay the same, except that we will have a more a better view of where velocity and or what velocity and acceleration are part of. But energy and momentum definitions are going to change, and that will be the major change that will happen. Okay, so but all this comes from all the way back. Let's talk about three quantities. So let's say, let me write this as G. Typically, we say this is ground. There is another point A, and there is another point B. This could be in three different directions in space, but just for simplicity, we are keeping it all in a straight line. And the moment I write it as a vector, it will generalize. But usually, it brings in a lot of non-triviality just by taking things on not on a straight line. And we will have all our considerations for in a straight line, but the general features are also available, but we won't do it here. Okay, so what does this mean? So there are some distances here, and what does these 3 points mean? There could be 3 masses here, right? 3 objects here. So this could be a person G, person A, person B, and they could be moving around. Right? They could be walking around on this street, which is a straight line, which is represented by a straight line. And we have, let's say, a distance here. There is another distance here, and there is another distance here. You can say this is the distance or position of A with respect to G, or you can say just say XA. So this could be X of A with respect to G. This could be X of B with respect to A, and this could be X of B with respect to G. And let me make it vectors. Even though it is one-dimensional, distances are sufficient if I put in plus or minus. But let me say these are vectors. But this is just an introductory thing. I will change my notations very quickly. So what are we talking about? If these people are moving around, or even if they're not moving around, at least from distances, it's very clear that we have X of BG, X of the position of B with respect to G is equal to position of B with respect to A. I'm writing the second one first and the first one second. So plus X of A with respect to G. And if you want, you can put in vector signs in there, and immediately you can make it a 3-dimensional object. And this is pretty clear, intuitively very clear. And when Galileo first time wrote this, there was no doubt about that this can be right or wrong. Now, the moment you say that these are positions of these objects, then they can change with time. Right? And what Galileo did was that, so I'm going to put these are going to change with time. So, or what Galileo did, let's say, is, yeah. So the question comes, if I were to put a time dependence in here, one could raise, are these times the same? Is there something called, this is the time with respect to G, this could be time with respect to A, and this could be time with respect to G. So is there any difference in times between these objects? Is there any such thing? But Galileo, when Galileo was working on this back before Newton, he had no doubts about this issue, and he said these are all the same times. So this is Galileo's. This is Galilean relativity. So what is Galilean relativity? Then let's say that B, G, and A are relatively at rest. each other. Like relatively means if G is moving, A is also moving. If G is at rest, A is also at rest. Because I say relatively because it depends on who is watching, right? If G is watching A, then A is at rest. But if someone else is moving, then G and A could be moving together. And B could be moving, and B is moving, and B is moving. Let's also say it's uniform velocity. So what we are trying to say then is that, is this within board space? Yes. So then what we are trying to point out is that x of B with respect to A is as a function of time is equal to velocity of B with respect to A times t. And the other quantities are just constants. So x of A with respect to G as a function of time, this is a constant. So together we can write x of B with respect to G as a function of time is equal to, I'll drop the t dependence in the second one. So this is B of B A as a function of time plus x of AG. But as I pointed out already, that this one might raise the question that are these evaluated at the same time or not? And the moment you raise that question, it is very hard to think how do we proceed on this, right? How do we actually derive a principle of relativity? Like if we have nothing to depend on, then how do we start this? And that's what we want to at least motivate today. And this was necessary, historically speaking, because all this was good, right? Galileo wrote this and made these assumptions and got this relation, and this was consistent. Whatever conclusions you came from here, right? Conclusions were consistent with Newtonian physics. By conclusions, what I mean is that if there are two frames, one is moving relative to the other, and you make observations of, let's say, physical quantities, you let us say you throw a projectile motion and it comes back in your hands. Everything is consistent if you use these equations to go from one frame to the other. So conclusions are consistent, are logically consistent, let's say. Logically consistent with Newtonian physics. By Newtonian physics, I mean F is equal to ma, right? Newton's laws of motion. And the idea that which frame are you measuring things from? Always in Newtonian physics, we have a frame. We often in the beginning, we don't stress on it so much because we don't want to confuse students, but there is a understanding that I have chosen a frame, which is usually your lab frame. You can always say there is another person who is moving with respect to the lab, with respect to a constant velocity, then are the conclusions going to be the same or not? And it turns out that if you use Galilean transformations to transfer one quantity to the other, equations will look different, but the conclusions will remain logically consistent. You're not saying number to number will match, but it will obey some transformation rules. Right? If this is the velocity, if you add the two velocities, you will get the other velocity, and that will match with the observation. So that's the idea of Galilean relativity. And the moment Maxwell's equation came up, so let me mention this, maybe write this down. So this was all okay until Maxwell wrote his equations in 1865, around 65. So in 1865, Maxwell's equation, which describes electricity and magnetism. So Maxwell's equation showed up, and one of the features there was that the speed, there was a speed, right? There was a speed which is now known as speed of light in vacuum, and that depended on some constants which were properties of space and time itself. In principle, space, right? Epsilon naught is the permittivity of vacuum, right? Imagine there is nothing in space and you associate a property to that. Like this is the, you can say in very simple terms, you can say this is the electric property of vacuum, of nothing actually, and mu naught is the magnetic property of that. It's related to what you know as conductivity, resistance. Those are all coming out of that. So if I ask you what is the resistance of deep space, right, or vacuum, like what is the resistance between 2 points in there, and that's what we're talking about. And speed of light turns out to depend on those properties, and it seems like this is a constant, right? Since it's a space property of space, it will be a constant. It cannot depend on the inertial frame. It cannot depend on the frame of reference. So that will actually violate Galilean relativity. And it was realized, they also found that is instead of Galilean relativity, that is what is Lorentz transformation. So what is Lorentz transformation and what is Galilean relativity? So let me first write things down. So this is Galilean relativity. It says that you have z prime is equal to z minus vt. Again, I said in terms of x that there were three quantities and one is moving. Same idea. If you were in a moving frame and two frames measure the coordinates of the same object, and this is moving, right? And if you do the same thing with a moving frame, what is the motion? So let me do that. So this is the prime frame. So this is your prime frame, and that's your, so let's say z prime, and that is z. And there is something happening, right? This is the event. Right? So this is observed by this frame and this frame, and the second frame I have given is moving with velocity v. And whatever physics you do in these two frames, they are connected. The idea is that if you use this transformation, everything is okay. Everything will be logically consistent. So this is t prime is equal to t, and there are two more, right? X prime is equal to x, and y prime is equal to y. That's Galilean relativity, very intuitive, and we learned this very early in our courses. Right? Now, after Maxwell, it was realized that there is what is called Lorentz transformation instead of Galilean relativity transformation. It is basically another statement of relativity, and that seems to be more appropriate. Same idea, z prime, z two frames that are moving, but if you want logical consistency, what you need to propose is the following. So there is a factor gamma that shows up. So that's gamma. I have difficulty writing it. So it's going to be gamma. And this is z minus vt. So very similar to what we have there. And here we will have t prime. So let me, instead of, so this is t prime is not going to be t. Instead, I will say, I'll put a c there in front. So just so that the dimensions matches. Or actually, let's not do that at this stage. So this is t prime is equal to gamma again times v over c squared times z, and there's a minus sign, plus gamma times t. Okay, So the time is no more, T prime is, no, oh, so it's T prime. Okay, so that's your Lorentz transform. We'll write it in a simpler way very quickly. Prime is equal to x, y prime is equal to y. So actually, just to get the symmetry out, let me rewrite this in terms of dimensionless variable. Let me multiply by c everywhere. And so this is better. So there's gamma times z minus beta times gamma, gamma and beta times gamma times c times t. So that is c times t coming in. And this is equal to minus beta gamma times z plus gamma times c times t. And why that is easier than what I wrote earlier is that you can remember it in the following way. Z prime ct prime is equal to gamma minus beta gamma minus beta gamma, and that's gamma. And x prime is equal to x stays the same. So that's your two transformation. And one says that, okay, what was the need for that? All that is are details, but we want to see if there is a third one, for example. Like, is there a third one? Maybe, yes, and at least we will motivate that. And is there only one speed limit? Like when you talk about a speed limit itself, there is this, it has to be one, right? Otherwise, it's not a bound. If you have an upper bound, that can be only one. Because if there are two of them, then one of them has to be less than the other. Right? So by definition, bound has to be one. But you could ask, why should speed of light be the bound? Maybe there is something else. For example, these days we have gravitational waves, right? And they also move with a very high speed and presumably speed of light. And you could ask, is it possible that two waves, like one is an electromagnetic wave related to electricity and magnetism, another is a gravitational wave related to gravity, why should these two have the same speed? Like, isn't that a huge coincidence there that they all have the same speed limit? And if it is, what is the source of that? So those kind of questions can be raised. And to that end, let's try to build this as logically possible or as simple with as simple assumptions as possible. Right? Currently, I have just stated Galilean and Lorentz transformation. Let me now sort of derive it based on some simple assumptions. Okay, so again, so now we are the derived principle of it. And before I do that, any questions at this stage? All that should be
No.
fine.
Yeah.
Okay, so now we are asking that is there a general transformation? So first we assume that x prime. Let's stick to just one dimension, right? Z and t. So there is z prime is a function of z and t. It could be in general any function, and t prime could be any function. So we are asking is that what are the possible solutions of these transformations, right? So again, we have this is your z prime and t prime, and there is another frame which is z, and there is some event happening, right? And we are observing that event. And what is the transformation connecting the two observations? That's what we are asking. So the first assumption we make is that this I want to prove, but one can think of it in the following way. If we have some equations today, you expect the equations to be true even 100 years later, right? Our equations don't change with time, right? That has to do with, or for example, if I'm using an equation here versus using the same equations on Mars, are the equations going to change? The equations are not going to change. Your constants like mass of Earth might has to be replaced with mass of Mars, but our Newtonian gravity is not expected to change, and that is called homogeneity in space. Right? So we assume, so let's say requirement one, let's say, is that space is homogeneous, space and time is homogeneous. Or in other words, there is nothing special about Mars, or for that matter, another galaxy over our galaxy. It's an assumption as of now, but to our best of our understanding, that's what is going to happen. You can also say it is isotropic in the sense that whether you're pointing in the north direction or making an angle with the north direction, your equations should not change. So based on that, so let's say it's homogeneous and isotropic. Isotropic means it is direction independent. That immediately gets rid of all these complicated functions here. It has to be linear. So this implies that the transformation has to be linear. Has to be linear. I couldn't, I don't have a very immediate way of proving that, but I think let me make that assumption instead of saying that I'm going to derive that. So let me say that is, that's an assumption I'm making, but one can see through it using some conditions that, oh, okay, if you're moving with some velocity v, or you just rotate your frame, what happens? So that immediately leads to the restriction, if it is linear, that this has to be a times z, but a could be a function of velocity v, right? Times z plus b, the velocity as a function of velocity of v, because remember that this is moving with velocity v, right? And times c times t, right? That's some dimensional, or just for dimensional reasons, I'm keeping that. And even though, like, when we are like c by construction is a new entity there, right? But let's say that that's some velocity that exists. And c times t prime is equal to, let's say, e of v times z plus f of v, and then this is ct. Again, maybe if you don't like the appearance of C, just drop it everywhere. And then the only difference would be that A and B, at this point, A and B are dimensionless, then A and B will not be dimensional. There's nothing wrong. And actually, the way, the spirit in which we are doing, C doesn't show up yet. Right? So let's get rid of it. So at this point, A, B, E, and F are not dimensionless. Okay? But they don't have the same dimensions. That's our assumption. In principle, if it is linear, I can also add a constant to this, but isotropy removes that, right? So we have to get rid of it. So that's our basic assumption in there. Okay. So now the second requirement you say is that if let's say if the event is moving with velocity, if z was the particle itself, right? So let's say if a particle at rest Yeah, a particle at rest with respect to unprimed frame. Or primed frame, let's say. No, I think I want to say primed frame with respect to a primed frame. So what are we saying here again? Am I in the view? Yes. So this is your frame, that's your second frame. And let's say this is at rest here. And this is Z, that's your Z prime. And this is moving with velocity V. So what will I measure if I am in the Z prime frame, and let's say Z prime, it is right on the axis, it is at rest. So this is Z prime is equal to 0. That's what you will, it doesn't change with time at all. It could be Z prime is equal to a constant, but if I say that it is actually set so that it is at the origin, that Z prime is equal to 0. But what will the second observer observe the equations for this? He will say that this is Z equal to V times T. Okay. Is that clear? What I'm requiring? So the requirement is that if, maybe I can say, if Z prime is equal to 0, then Z is equal to Vt. That's a very special event I'm talking about. Like these equations are true for any event. I'm talking about a particular object which is at rest with respect to Z prime. It will look as if it is moving. So this should be satisfied in these equations. Is that clear, Ken? What I'm suggesting? I cannot hear you actually. I see you are getting unmuted, but I don't hear you. But you probably can clearly hear me.
Hello?
Yes, I can hear you now. Yeah, can you say that?
Yeah, no, I get what you're saying.
Okay. Okay.
Sorry about that.
So this should be valid in this. So let's see what that suggests. So we just have to look at the first equation, right? Second equation requires time. Let's stick to this. So this statement affects only the first equation. So what we are saying is that Z prime set it to 0. That's it. So this should be satisfied by that. And that's equal to A of V times Z is Vt. So that's Vt. Let me drop the velocity dependence. That was just to highlight that. So this is A times Z is Vt plus B times T. These equations are valid for any process. For this process, it seems to suggest this. And we immediately learn, oh, that means that A has to be, or B has to be equal to minus A times V. These are like initial conditions, right? When we write a differential equation, we get solutions, but then we say that, oh, this has to satisfy this. So we learn something about the variables, right? So that's something like that. So for this particular process, we learned that, A must be equal to BV. So we immediately conclude. So this now suggests, just based on that, we have learned that since B has to be equal to minus AV, so this must be A times Z minus VT. And we still don't know much about the T prime, so that's E times Z plus F times T. Okay. Just by requiring that something moving with something that is at rest at Z prime should be behaving as if Z is equal to VT in the other frame. That's the requirement we have. Okay, what next? Next, let's say that, so this is going to be another requirement now, a boundary condition in a sense. So we say, so this is third. First we said homogeneity and isotropy. Second we said something at rest in one frame should look in the following form in the other frame. And the third is now, let us say, so we're talking about an inverse now, right? So this is a requirement regarding inverse. So what are we suggesting is, suppose I have this, that's your z prime, move with z, that's your velocity v, and it observes something. The same thing can also be thought of as, that is a z prime, moving with an opposite velocity, that's z, and that's also a possibility. And we would say that whatever our transformations are, so that's your velocity v or minus v. So we are going to say that whatever our transformations are, it should satisfy the following things. That if I were to flip the velocity in those equations, so flip the velocity to minus v, and at the same time swap z to z prime. Swap all the z and z prime. Wherever I see a z, replace it with a z prime. And wherever I see a z prime, replace it with z. And do the same thing with time, t. So this is and. Okay, so that's again a condition I put on my transformations. So let's see what is the implication of this, and the hope is that we can learn something about this about these coefficients. So what does this imply then? So we have, remember, we have z prime is equal to a times z minus vt. Right, that's what we have concluded from the first two assumptions. Not talking about the t prime, let it stay as it is. If I were to use this prescription that this has to remain the same under these conditions, so I replace z prime with z, and maybe I should say something more. Yes, so this is equal to a. Give me a second, okay? Yeah, so notice I have to stress this a little bit. So what I'm getting is that there is a of v here, and this is z minus vt. And if I swap all these quantities, z prime is z, and a gets replaced with minus of v, and this is z prime minus plus this time, plus vt. Okay. So what are we saying? If I were to replace these things, this should not change, right? I mean, except for these change, I should have this a of v exactly equal to a of v minus v. So this implies that a of v has to be equal to a of minus v. So that means it is an even function. Right, that's the conclusion we are making. So I don't have to worry about it's minus b, so it's a positive function. And what else can I include from that? There's more things I can conclude. So this is not a fourth requirement I'm making. So let's say digression, right? So let's say I'm going to digress at this point. This is not an additional requirement. So this is a digression. And what is a digression? We'll bring in Galileo. What would Galileo have done at this time? Right? So Galilean relativity. So as of now, what we have is that z prime is equal to some even function a times z minus vt, and there is an additional t prime which I haven't made much progress at all. It is plus f of t. Right? We'll keep it as it is. We will worry about this. And we have also learned that because of this inverse transformation, so z is equal to a times z plus vt, z prime vt prime. What does Galileo come and say? He says that t has to be equal to t prime. So that's an additional condition. But I'm not going to use that condition because that's why it's a digression. You're going to get Galilean relativity right away from this, just based on these three assumptions and t prime equal to t. And if we see, if I put t prime equal to t for both, for all observations, then I have to replace this t prime equal to t. So then I just add it up. So first, let me add these two equations, and I get z prime is plus z is equal to a of z prime plus z, and d of t cancel out because t is equal to t prime, and immediately you get a is equal to 1. And if you put t prime is equal to t here, then it is very clear that e is equal to 0. So this implies that e is equal to 0 and f is equal to 1. So suddenly you know everything, all the terms, and you conclude that Galilean relativity says that z prime is equal to z minus vt and t prime is equal to t. Right. Again, what we have used, our homogeneity in space and time. A particle at rest in one frame should look like z equal to vt in the second frame. And the third one, a particle going in the opposite direction should look, as far as equations goes, they should look very similar, right? Exactly the same equation should come up, except that we have to replace z with z prime, right? That's our Galilean. But now we want to get away from the digression and come back, and we will put one more condition. We have put three conditions as of now: homogeneity, a particle at rest, and particle moving backward from the original direction. And the fourth condition is, before I say, any questions at this stage?
No questions. Thank you.
So, okay. So the fourth condition we put in is about light, right? So again, we have, as of now, we have, which I've already written, I don't want to repeat it here. So let's say motion of light, or motion of light is identical to both observers. What does that mean? That First of all, light is moving with uniform velocity. That means that if the first observer says z prime is equal to ct, the second will say that, and z is equal to ct. Both say the same thing. And it, of course, assumes that at time t equal to 0, they were at the, like, at time t equal to 0, the origins of the frames overlap. Correct? That's one thing we have used in here. Is that clear? That's a requirement we are putting.
Yeah, yeah.
If I require that, now let's go back. So we already had z prime is equal to a times z minus vt. I also have the requirement that in the other, if I look at it as if it was going backward, this is a times z prime plus v times t prime. So the idea is use them here. Use these two quantities in there. So this equation should respect the speed of light idea also. And let's substitute it in there. So we will substitute it here. So that's z is equal to a times z prime is ct. And let's replace both the equations, sorry. So that's equal to, let's write everything in terms of t and t primes, right? Oh, sorry. So this should be z equal to t prime, right? Sorry. So I made a correction here. Is that clear?
Yeah, yeah.
That was a mistake. So this equations becomes c times t prime is equal to a times c times t minus v times t. And this is c times t is equal to a times c times t prime plus v times t prime. Right. This would imply that t prime, so what I can do is, yeah, so let me write this as c times t prime is equal to a times c minus v times t. And let me put this in the opposite way. So this is a times c plus v times t prime is equal to c times t, right? So this leads to that, this leads to that. Clear? If those two equations are to be the same, you divide them out, right? T prime cancels out, t cancels out, so we should have c over a times c plus v is equal to a times c minus v over c. So that gives an equation for a, and that is that a is equal to 1 over 1 minus v squared over c squared. Right? If that is the case, so certainly we have a is known, and if a is known, let me go back and put it in the time relation. Correct? Can we get something about E and F out of this? So let's see. Yeah, so we had T prime is equal to E times Z plus F times T, right? That was our relation. Now we want to solve for E and F, right? Because now we have A, and T prime is Z prime over C where z prime itself is, so this is z prime over c because of the speed of light. Motion. And z prime itself is a times is that correct? Am I missing something? Something tells me that I'm missing something. So A will be equal to E. Okay, again. Okay, let's go slow. I think I'm mixing up things. Okay. So what I have at this point is, yeah, so let me conclude here that what we have as of now, so thus, right, thus we have z prime is equal to A, which is known, times z minus vt, and p prime, which is equal to E times z plus f times t.
Why do you think you're missing something?
Yeah, probably nothing actually. I don't know. I think I got worried when I was doing that. Okay, let's do this again. Sorry. Okay. I think I was missing a term there, so I thought I made a mistake. But maybe it's just overlooking at the answer. I shouldn't be looking at the answer, right? So as of now, it's all fine. So we have found that A is equal to 1 over B square minus C square, right? That's our conclusion. Now, what else can I do? I would like to now, from this point on, solve for E and F, correct? That also needs to be done. So let's again use our idea that yeah, can I do something with this? Yeah, and let's also have this feature that I also have Z is equal to A times Z prime plus VT prime. So let me solve for T prime from here and then Z prime from there. Okay. So let me do that. Yeah, I think that's what I wanted to do actually. So I think earlier I was not taking. So this is all okay. We also and, right? And I also have, because of that inverse relation, I think I will use this plus VT prime. Okay? That should be fine. I think, sorry about the confusion. Okay? So now
So
let
you
me,
wrote.
yeah, go ahead.
Sorry. So you wrote that previously
Yeah,
for the inverse.
yeah, this was for the inverse relation, right? Right. That was coming from all the way back. Are you seeing it in your notes or should I show you?
I can't see it in my notes. I have z equals a. I must have messed up.
Okay, here. So here we said the inverse, correct? And we can put
Right.
it, right? So z prime was z minus vt times a. Z was a times z prime plus vt prime, right? Switched.
Oh, I see. I see. I see.
Okay. So just by flipping that, we require that actually. Okay.
And then that. Yes. Yes. I see. Where the a minus. Yeah. Okay. Sorry. I didn't. Yes. Thank you.
So I'm going back now, and now that we have learned what A is, now I want to talk about P primes. And again, I want to invoke that condition there. So I will use these two. So the idea is that I'm going to put P prime here, Z prime in there. Right. So substitute these two in this. Okay. So I will get, let me write that down here itself. And so this is Z is equal to A times V prime is A times V minus A times V times T, and plus A times V and T prime is E times Z plus F times T. Good.
Good.
So I have two relations. So I have to compare all the coefficients of Z and T, right? If I compare all the coefficients of Z, I get 1 is equal to A square, and then there is AVE plus AVE. That has to be true because this is true for any Z and any T. And the second is that comparing the coefficients of T, this is equal to 0 is equal to minus AV and plus AVF. Now A square V times AVF. So the second relation immediately implies that F is equal to A. I got one more done, so we are remaining with E, but E I can solve using this. Is that clear?
Yes. Yeah.
So if I had to move my board, are you still writing? Can I move it?
Give me 3 seconds. I'm sorry. Okay. Thank you.
So we have 1 is equal to A square plus AVE. So E is equal to 1 minus A square over A times V. So we just have to do the algebra at this stage. That's 1 minus 1 over 1 minus V square over C square divided by V over 1 minus V square over C square with a square root. So that's the same as 1 cancels out. So there's a minus V square over C square divided by V, and there's a square root remaining, right? So it's 1 minus V square over C square. One of the V cancels out, so E is equal to minus V over C square times A. A is 1 over 1 minus V square over C square. So after all this, what we have learned is that our transformations are pretty much fixed. So we have Z prime is equal to A. Let's start writing A for gamma, right? That's a standard notation is A for gamma. So that's gamma times Z minus of Vt, but instead I will multiply and divide. So let's say A is gamma and beta is V over C. So I multiply and divide by a C. So that's beta times gamma times C times T. And the other relation is T prime is equal to minus V over C. That's minus beta times gamma times Z over C. And then there is plus F was gamma, right? So that's gamma times T. Multiply throughout by C, so we get C times T prime is equal to minus beta times Z plus gamma times C times T, which can be written as, like writing it as a matrix. This is Z prime, CT prime, gamma minus beta gamma, minus beta gamma, and gamma. Where beta again is V over C and gamma is equal to 1 over 1 minus beta squared. Beta is always less than 1, or we will require it to be less than 1. It's not that it is implied by these transformations. We will say this will be less than or equal to 1, primarily because there are logical inconsistencies. If you start going faster than light, you can actually go back in time and pretty much kill yourself, right? And then all those, it's not logical at all afterwards. So just to stay away from that, we require that B has to be less than 1. And this has to be greater than or equal to 1, because if beta is less, it's in the denominator. That will go up, go greater than 1. That will be called the Lorentz factor. So again, if I summarize, based on some very simple requirements, that first of all, space has to be homogeneous. Second, that if something is at rest, it should have the following equations. Right? So that means to say my hand should not behave in a different way than my nose, right? That's kind of because my hand is at rest with respect to me. So that sort of logical requirement. And the second is inverse, whether I'm moving forward or I look backward and reverse the whole thing, my equations should look exactly the same. So based on this, and the important condition is that speed of light should remain the same in two observers. Just by using that, you can get the Lorentz transformation. And even though I haven't shown it, one can require that if you require causality, causality means that whatever I said, you cannot go back and kill yourself. That means to say past affects the present, but the future does not affect the present. So that's an assumption we make just because we don't understand the logic of how things behave in that. And that will be called causality. And the idea is that if you have causal behavior and Lorentz transformation, then there can be only one speed of light. That means to say there's only one maximum speed. Like you cannot talk about two things simultaneously. Like I said, gravitational waves and electromagnetic waves both could be having two different speeds, and there might be two different transformations. Or is there another? So we have Galilean relativity, that is Lorentz relativity. Is there a third relativity at all? Is there something else you can cook up? And the claim is no. If you want it to be causal, these are the only two possibilities. Okay. I'll stop at this stage. We'll come back and talk about the implications of Lorentz transformations, basically all the ideas that we learn in introductory physics, Lorentz contraction, time dilation, velocity addition, and so on, and go ahead and define velocity. And then we will start acceleration on the next class on Tuesday, and then talk about forces and energy and momentum on Thursday. Okay, is that good? Any questions?
Yeah, that's great. So, so when you say causality, you're like it's referring to the cause and effect, right? So because there's cause and effect, you need only two.
Yeah, and that is an assumption we make in all of physics. It is, we assume that if there is a cause and effect relation, like I shoot and then someone dies, it cannot be changed in a different observing frame. For example, in my frame, I noticed that, oh, there is a friend of mine shot a bullet and another friend died, and another person sees the same event and says that no, the person died and then the person shot the bullet. That's not causal. If that was possible, that's not causal.
I see.
We assume that any physics that we observe, if it's a cause and effect thing, it cannot be changed. It has to be invariant. Like every observer should see the same cause and effect relation. They might see it in different times. One might say that, oh, it happened 5 seconds later. The other might say that it happened 10 seconds later. But if first you're born and then you die, you don't die first and then you're born, right?
Right. No, that
You
makes
don't
sense.
go reverse in time. So it's a big assumption we make. Yeah.
Yeah, it's very interesting, especially like when you think about gravity being like a wave and a particle per se.
Yes. Yeah. All these are serious implications, and logically, it gets intertwined very quickly if we allow non-causal things, then it's a mess, put it like that. Very hard.
I see. Yeah. I mean, there's no order, right? So.
Exactly. Yeah. There's no order. Yeah, that's correct. Yeah. Like, how do you comprehend the fact that you can kill yourself? And like, the movie's made, that's all nice, but when you really come on the table and talk about it, it's kind of, oh, I died, but then how am I existing? So it's kind of contradictory in nature, in a sense. So
Yeah, that's very interesting.
yeah.
So I just this might be digressing, but I'm just curious. Because time and space are so interlinked. I mean, I don't think that when Einstein came out with that stuff, he thought of gravity as a wave or a particle, right? I mean, he thought of it as like the fabric.
Yes, that's correct. And even the fabric itself. See, that his main idea was that he understood Maxwell's electromagnetism to such a detail that he was ready to interpret this as a property of space and time instead of as the property of vacuum.
I see.
What everyone did at that time was that it was, and again, it was very intuitive, because think of sound, right? What do you do in sound? There is a sound, and sound travels in a medium, and the medium itself can have a velocity, correct?
Right.
The sound speed depends on whether you're moving in air or whether you're moving in solid.
Right.
And the moment Maxwell wrote down C is equal to epsilon naught mu naught, which is a property of the medium, everyone compared it with sound. Oh, so our vacuum is a medium. It has some properties. And you associate a property to that, and you start measuring properties of that. But the remarkable thing was that this did not seem to have any property. This was really absolute, or this was not absolute. Like, it's not that C is actually the property of space and time. It's just, it happens to be like that. It is more than that. So Einstein was able to get off from there and say that this is actually more fundamental and this is something to do with space and time.
I see.
And that was a big leap he made because everything existed. Notice Lorentz transformation existed, velocity addition existed, everything
Yeah,
existed.
yeah.
And they were really struggling with all these equations. All these equations existed, but no one was ready to make that conceptual leap, which kind of freed the whole theory. And that was a big leap. And that was the special relativity. That's the principle of relativity, which involved changing the definition of energy and momentum. And next came the idea that, okay, so this is all when you're moving with constant velocity. What if you were accelerating? Then how does things change? Like even, I shouldn't say not just accelerating. How does inertia look like in, how do you combine inertia with principle of relativity? Maybe that's the way to put it. Inertia, remember, has to do with mass.
Right, right. All of it has to do with mass, right?
And that led to the idea of general relativity. That's a second step, and which again was very hard for Einstein. Like it took time to grapple with it. Does that help, roughly?
Yeah, yeah, yeah. It's just it's really fun to think about that kind of stuff, especially like in regards to gravity and time.
Yes,
So,
of course, of course.
well, thank you so much, Dr. Shajesh.
Okay, good. Keep asking questions. Yeah. Okay. Thanks. Bye, Ken. Yeah.
Oh yeah, bye. Good luck with your talk today. If I don't
Thank
make it.
you.
Yeah.
Sure, sure.
All right. Goodbye.
Yeah.